The Isoni SLA Manager is the single access point to the Isoni. It receives the technical SLA with the Virtual Service Network description. It contains a description of all service components, virtual links and storage objects for the application. This includes, for example, the CPU power, amount of RAM, the required bandwidth, or the size and access speed to the long-term storage. The SLA Manager checks the PSLA and extracts the VSN descriptions for further processing and pre-reservation. It sends it to the Deployment Manager, which is aware of all deployed VSNs within the Isoni domain. It instantiates a specific instance of this Deployment Manager for this particular VSN and starts the domain-level availability check. The Resource Manager domain checks the Isoni nodes for sufficient computing resources. The Path Manager domain checks for the connectivity and quality of service constraints for the virtual links between these nodes. If a matching constellation is found, the nodes get assigned, and the VSN description is passed back to the Deployment Manager. Depending if the VSN is spread around the different Isoni nodes, the Deployment Manager splits the VSN description up in different sub-VSN description and pass them to the corresponding nodes. Let's assume we only have one node assigned. The Resource Manager node passes it to the Storage and Path Manager. They do the internal pre-reservation. On the domain level, the Deployment Manager collects all pre-reserved requests and introduces the SLA Manager to do the offer for the requested deployment. On a commit, the path through the infrastructure is the same like for the negotiation. All resources are now booked and the VSN is ready for the deployment. When it is time to finally deploy the VSN, the Resource Manager node prepares the virtual machine units and passes them to the assigned hosts. The Resource Manager node sets up the execution environment and configures the scheduling, storage connections, virtual interfaces and other parameters from the VSN description. The Path Manager node introduces the Isoni Exchange box to set up the virtual network and deploy the scheduling for the network traffic. The Storage Manager provides the connection to the assigned long-term storage. Now the VSN is ready to run and the framework services can trigger the application workflow.
Let us now focus on the networking aspects of Isoni, providing networking infrastructure as a service. Isoni provides networking connectivity among application components and to external networks like the Internet as requested and modeled in the VSN description, which is part of the DSLA negotiation as introduced before. Isoni supports best effort and loss-tolerant real-time traffic and allows to specify certain quality of service attributes with it. These quality of service attributes are related to bandwidth and especially for loss-tolerant real-time traffic like audio and video, to delay and jitter. The path management of Isoni takes care that the appropriate transport network resources are allocated. Isoni itself relies on different kinds of transport networks. These are best effort networks, routed IP networks providing different kind of QoS, and at least leased lines. Depending on the specified virtual link requirements, Isoni is in a position to lead the virtual link related traffic on capable network paths satisfying the QoS requirements as required by the customer. So, Isoni manages different kinds of available transport network resources against VSN deployments requested by the customer. In a successful case, all the required resources are reserved and allocated. Depending on the QoS attributes, the network traffic of deployed application uses individual appropriate network paths on heterogeneous transport network infrastructure. How Isoni is able to provide these kinds of QoS attributes for automatic deployments. Here an abstract network model is depicted showing the several VMUs and their network connectivity over physical hosts and node architecture hierarchy. As shown here, VMUs of the same or different deployments may share the same physical host. To avoid any impact of concurrent VMU traffic, the bandwidth of each virtual link has to be controlled, in other words policed. Isoni follows the principle of managed infrastructure, which means that the network traffic load of each multiplexing stage is managed. A gapless policing ensures that multiplexing stages, so-called IXBs, always get a controlled load of traffic. Therefore, bandwidth policing is essential for Isoni to ensure QoS for individual virtual links. Any overload would cause unduly controlled growing of loss rate, delay and jitter, jeopardizing real-time applications. Also, non-real-time application data throughput, usually based on TCP, strongly decreases with growing delay and loss rate. The transport network paths carrying real-time traffic are continuously supervised using one-way measurements for loss, delay and jitter, especially on paths between Isoni nodes. This abstract network connectivity view has also been implemented in the prototype of Irmos project. It shows the two transport networks of the testbed, one foreseen for carrying the best effort traffic, and the other foreseen for real-time traffic. For each path, the health status is supervised by doing one-way delay and jitter measurements. Also, the loss rate of the test traffic is measured. Status aggregation of the path health simplifies the general view. This view is not very practical in day-to-day operation, so the next view is more useful. The best way for a general view of internet network connectivity offers a connectivity matrix. Each intersection point represents the possible connectivity between Isoni nodes in general. This view represents the prototype health status graphical user interface. The first three nodes, A, B and C, have two interfaces, one for accessing the best effort network and the other for accessing the real-time network. The points of intersection represent the path health status of Isoni path, which represents the path measurements for delay, jitter and loss as introduced before. Node D represents the transit node for accessing the internet. Therefore, node D just has one interface carrying best effort traffic. Reachability of VMUs by assigning public IP addresses is supervised by Isoni as well as the reachability of external resources for which deployed application relies on. To be able for detecting any outages or connectivity problem inside a node, also operational and reachability status of each node is supervised by Isoni. The status entry represents the physical host of a node. Finally, on the right side, the availability of network resources per QoS class is indicated, which will be part of the next version of implementation.
Let's have a look at a real deployment. The graphical user interface for the execution environment shows the three different Isoni nodes we currently use. On the top, you can see the aggregated resource informations of the domain level. Based on this information, the Resource Manager domain chooses the node to assign. In the center, you can see the node level view and each physical host. There is already a VSN running and you can see the virtual machine units on the physical hosts. When a reservation request arrives, the Resource Manager node reserves the resources, as you can see indicated in yellow. After the final booking, the resources are turned red and are ready for the deployment.
Irmos data storage, a part of the Isoni infrastructure, is provided within each node of the demonstration testbed using a high-performance clustered storage system. Each storage node connects to each host and application service components running within virtual machines using an InfiniBand network. Disk-based data storage systems are essentially serial access electromechanical devices with significant limitations in latency and bandwidth. Our task is to predict the performance capability of the storage system such that quality of service can be guaranteed even when it is shared by multiple users. We have integrated complex models of the behavior of the system to enable this. This monitoring tool shows how a storage pool has been created for the raw digitized video material for the post-production demo application. This has previously been negotiated via the SLA managers to provide 2 terabytes of capacity and up to a total of 200 megabytes per second of bandwidth. The management tool allows us to simulate a further request for storage for a 24-hour period in the future, but during the time the existing application is running, we will request a 500 gigabyte pool of data storage with a bandwidth need of 80 megabytes for use by a video application. Observe, the total allocated bandwidth has risen to 280 megabytes per second, but also, and more importantly, the capability of the system has been significantly reduced due to the interaction effects which have been modelled within the storage manager. This is referred to as the system quality of service capability and is a function of the demands, access profiles and interaction between users. If we now make a further SLA request for bandwidth from the storage pool, we can see it exceeds the capability of the system and will normally be automatically rejected and rolled back during the technical SLA negotiation phase. Finally, we can see the system operating normally with multiple data connections to the storage pool for the post-production application. Each connection monitored will be regulated and throttled such that it does not exceed its requested performance and interfere with other users of the resources. That's all, folks.
Back to the view on the deployed VMUs. After the execution, the VMUs are turned off and the resources are freed.